Let us move on to our next speaker. His name is Arighna Pan. He is in second year of integrated PhD. He is from ISER Tirunanthapuram. His topic for the day is derangement. Arighna, over to you.
So, to start with this topic on derangement, so first of all, we will denote first n natural numbers as box n, and then a permutation on first n natural numbers is a set of I1 to In such that Ij is from box n and Ij is not equal to Ik for all j not equal to k. And a derangement we will call a permutation of box in, we call it a derangement if ij is not equal to j. That means the jth position is not taking value j. That means there is no fixed point for all j in that first n natural numbers. And for this case, we will denote the number of derangement as dn, namely this one, or maybe subfactorial of n. These two notations are used for number of derangements from a permutation. First, this problem was supposed by a French mathematician Pierre de Montemort in 1708, and very like within 3, 4, 5, 4, 6 years it was solved by again Montemort and also Nicolas Bernoulli individually, and they both used uh, principle of exclusion and inclusion. And mainly whatever the problem was supposed by Montemort, it was mainly a head check problem. To discuss derangement, mainly we use head check problems, secretary problems, and these type of problems. So first recall what is principle of inclusion and exclusion. So if A1, A2, An are subsets of some finite set A, so then by C formula we can say the cardinality of A1 union union An, it is of this form. It is by like first count all the size of AIs, and then discard that whatever you have over counted, and again add something that you have already deleted, and continue this, and you will get this type of formula. And if we like uh, take if we do some more calculation, we will get that cardinality of A1 complement intersection intersection with An complement is just by de Moivre's formula, that is just complement of A1 union An, and which is equal to size of A minus size of A1 intersection, sorry, A1 union An. And from the C formula, we can find this type of structure of this, the value of A1 complement to the intersection An complement. So here I am taking another problem for derangement to discuss the derangement. So okay. So what is the problem? So it is said that at a banquet, there is a banquet of a large conference, 8 mathematicians hang their coats on the coat rack as they enter, and at the end of night they live in a drunken stupor, each one randomly putting a coat without checking. So we have to find the probability that none come back home in their own coat. So mainly the problem is they don't pick their own codes. So they in that case there is no fixed one, right? So in this way, so we'll this try to solve this problem, and we'll try to find the probability. So whatever the problem is, that is we have to find that they come back home in their own code. So to apply principle of inclusion and exclusion, we should look into that the complement of this event. And what is the complement of this event? There exists that is at least one mathematician comes home back in his own code, right? Okay. So so we denote that AI by the set of all the ways that ith person picks his code. That means we don't care about the other person, but ith person always picks his code. And these AIs are subset of a finite set A. And if we ask that what is A here, it is the all the ways that any of n codes get picked by any of them. Okay. So now what is the size of AI then? Sorry, what is the size of AI then? That should be n minus 1 factorial, right? Because I person is getting his code that is fixed, but the rest of the n minus 1 codes getting picked by n minus 1 mathematicians randomly. And there are everything, we have n minus 1 factorial many choices. And if we vary that the value of I, that should be n choose 1 into n minus 1 factorial. Why? Because I have to pick I from n, right? And that we can pick in n minus n choose 1 many ways. And then by multiplicative rule, we will multiply n minus 1 factorial with n minus n choose 1. And if we do some more calculation, it will become n factorial. And similarly, yeah, we have overcounted something. Why? Because when ith person I am picking, ith person I am fixing, we don't care about what the jth person is doing. Jth person can pick his own code. Maybe he is not picking his own code. We are not taking care about. But if jth person is picking his own code, in the ith case we are considering it. And also, when we are considering the jth case, this case again getting overcounted. So what we have to do? We have to delete that the case where I and jth person picks their own code and the other we don't care. So we have to take that AI intersection AJ this thing out. So what is the choice of what should be the size of AI intersection AJ? Because two persons are picking their own code and the rest of n minus 2 I don't care. They can be picked by anyone and that can be done by n minus 2 factorial ways. But obviously I not equal to j, we should taken care about. And if we take the all, if we vary that ij for all ij's in that third bracket n, you take the summation and it should be n choose 2 into n minus 2 factorial. Why? Because we have to pick I and j only. Rest of the other rest we don't care. So that 2 can be picked in n choose 2 ways. And by multiplication rule, we will have this summation AI intersection AJ should be n choose 2 into n minus 2 factorial. And after again some calculation, we have n factorial by 2 factorial. So for the general case, if I pick some k many people are picking their own codes, that should be like in the similar way, it should be n choose k into n minus k factorial. And again by some calculation, we should have this is n factorial by k factorial. Previously, I have said that what is A? A is just that all the ways that n codes get picked, and that should be done in n factorial many ways, right? And also we have said that they are not coming back in their own code. That is complement of that at least one of them are coming his own code. So what is that? That is A1 complement intersection AN complement, and that is the number of derangements in this problem, right? So the so in the in the section of principle of inclusion and exclusion, we have derived a formula, right? And what should it be? It was the size of derangements. It was the size of A minus A1 union A2 this thing, and which is equal to this thing, right? That we had. So what will be our DN? Our A size of A is n factorial, and as we have calculated that what is the size of this thing? It is just n factorial minus n factorial by 2 factorial. Again, we have to add that three people case, and again so on. So everything we will have n factorial. After some calculation, we will have this thing, that is n factorial minus n factorial by 1 factorial, and the nth case it will be minus 1 to the power n factorial by n factorial. And if we calculate this again, it will be summation I to 0, summation I is equal to 0 to n minus 1 to the power I into n factorial by I factorial. So what is the probability? The probability is just by all the possible events, all the OS of the possible events by size of sample space. Sample space is n factorial, right? Because n factorial is the number of OS that any code can get picked. So the probability it will be what we had. We had factorial n is equal to summation I is equal to 0 to n minus 1 to the power I n factorial by I factorial. So if we calculate it, it will be summation I is equal to 0 to n minus 1 to the power I by 1 by I factorial. And that is our probability. But the most interesting case, if we take the limit on this Pn, if we take the limit on this Pn, then it will be summation I is equal to 0 to infinity. Obviously, n is going to infinity, and which is an identity. That is the expansion of e to the power minus 1, and which is around like approximately 0.3679. So, if we take some derangement from a permutation, there is a pretty much big amount of chance that we will get a derangement. That is around 37%, right? Okay. So from this thing, we can why should we have that thing dn sorry pn if you take the limit converts to in 1 by u. So we can from the derangement number we can derive this thing in this way. It is very easy to derive. Like if you take this this value, it will be nothing but n factorial into minus 1 to the power n plus 1 factorial, and so on. And if it is clearly less than equal to n factorial, 1 by n plus 1 factorial, 1 by n plus 2 factorial, and so on. And if we multiply if we bring that n factorial inside that bracket, it is nothing but 1 by n plus 1 plus 1 by n plus 1 into n plus 2. Then next one n plus 1, n plus 2 into n plus 3, and so on. Right? Now, just take that 1 by n plus 1 out of this bracket. It will be 1 by n plus 2 plus 1 by n plus 2 into n plus 3, and so on. Clearly, we have that n plus 3 is greater than n plus 2, right? And it is clearly n plus 2 is greater than 1 by n plus 3. Just use this thing in this place, and clearly we will get a strict inequality, that is 1 by n plus 1, and which is in this part it will be 1 by n plus 2, then next will be n plus 2 whole square, and clearly it is a GP series, right? With a common ratio which is less than 1. So if I apply the formula for summation of GP series, it will clearly give n plus 2, n plus 1 by n plus 1 whole square. So the first part of the inequality is done. It is very easy, right? And then for the next part, this thing, it is much more easy. Why? Because just bring it here and bring it here. We will have what? We will have n square plus 2n, which is which is less than n plus 1 square. And this inequality always true because it is n square plus 2n plus 1, right? It is always 1 greater than n square plus 2n. So this inequality is also true. And 1 by n is always less than equal to 1, that is also true. So these inequalities done. So for so if the first inequality is done, then clearly we can say that dn is nothing but the nearest integer of n factorial by e. Why? Because for one case it is fine, right? For d1 it is just 0. It is very easy case. What if is n is greater than equal to 2? Clearly 1 by n is equal to, then what? 1 by n is greater than less than equal to half, right? And this, from the first inequality we have, that is less than 1 by n, which is less than equal to half. So if you obviously dn is some number of ways, it should be an integer, right? So if I considered some m and m plus 1, there are maybe dn should be equal to m, or dn should be equal to m plus 1, because it is an integer, it should take as some integer values. But what we have, n factorial by e minus dn is less than half. This length is 1, and this length is half. So n factorial by e must lie inside like either this place or this place. Okay, and as dn is an integer, it should take either less than half, so it should take this value. It can, if it n factorial by e is here, it cannot take this value, it should take this value. Or if n factorial I is n factorial by e is here, it should take this value. It should not, it cannot take this value, because it is less, the length is less than half, right? It, this length is less, not less than half. So it should take the nearest integer value, right? So this too we can see that what we are getting from the like derangement. And there are some recurrence relation also, that is uh, if we have d1 is equal to 0, d2 is equal to 1, then for n greater than equal to 3, we should have dn is equal to n minus 1 into dn minus 2 plus dn minus 1. Okay. So this thing is also very easy. Just add, let me add some paper here. So why this should be true? So if dn, that is number of derangements for n many elements, right? Or first n natural numbers. Okay. So if so this, maybe this is one first place, second place, third place. It may be kth place. This is n minus 1 place, and this is n. As it is a derangement, in nth place, it cannot take value n, right? So it should take value from 1 to n minus 1, right? So for the nth place, we have n minus 1 many choices. So what if n is taking value k? N can takes value k. That is, maybe we are like, without loss of generality, we are fixing that in nth place we are putting k. But then in the kth place, there also cannot be k, right? So we are dividing the whole thing in two cases. Either in the kth place we have n, or some p which is not equal to n, which is not equal to k. If this is if kth place is taking value n and nth place is taking value k, so it is fixed, right? As it is fixed, we have to consider only the derangements for the rest of n minus 2 places. And for the n minus 2 places, we already have number of derangements is equal to d of n minus 2. So for the first case, we have derangements d of n minus 2. And for the second case, if that kth place we are not having n, then we should have considered the all the derangements for first n minus 1 places, and that is Also the derangement, that is we are dn minus 1. So by addition rule, there are two ways, and total number of derangement should be equal to dn minus 2 plus dn minus 1. And this is when in a place we are picking value, we are fixing value k, but there are n minus 1 many options, right? So we multiply this whole thing by multiplication rule by this. So what we have established, that is dn is equal to n minus 1 into dn minus 2 plus dn minus 1. There are also many recurrence relation you can get through. Maybe I should. Yeah, I am done. For the yeah, if you want to study more, you can go with, like, there is a famous article by Mehdi Hassani, that is derangements and application. And also you can go through by Peter J. Cameron's derangement and p elements of permutation groups. And also like there the from 2003 Bulletin of American Mathematical Society. You can go through that on a theorem of Jordan. Yeah, yeah. Thank you.
Yeah. Any questions from the audience?
Mm, I want to ask question to Arighna. Uh, he was telling that the expression for dn is an integer, and he's like claiming that since we are uh, like it is some number of ways of choosing something, so that's how we can prove that this is an integer. But forget about the derangement. So looking at the expression that n factorial into that summation minus 1 to the power I divided by I factorial. So from that expression itself, can we prove that this is an integer, like in some way?
Uh, no, but maybe by it is by the definition of derangement, right? This is the number of ways. So number of
Yeah,
ways, it should be an integer, right?
yeah, that I know. Your claim is correct. That is an integer, but
Mhm.
I mean there are some proof like for binomial coefficient that n choose k. So there are some proofs of integrality of the binomial coefficient. So I want to ask you that is there some similar proof for this
Yeah.
integrality of the
So if you see the formula for dn that we have derived, that is n factorial minus n factorial by 1 factorial. N factorial by 1 factorial is an integer, right? That is true because n is obviously greater than 1 I am taking. Again,
yes,
then the next term was plus n factorial by 2 factorial. Again, see, the n factorial by 2 factorial should be an integer, right?
yes,
Because n is obviously greater than equal to 2 I am picking. And continuing this, the last term was minus 1 to the power n into n factorial by n factorial. It is nothing but just a minus 1 to the power n. That is also an integer. So the how we are deriving the formula we are getting for dn, that is some addition and subtraction of positive integers only, right? So it should be an integer.
yes, yes, yeah, 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 got it.
Yeah. Any other questions? Okay, then let us thank the speaker. Thank you, Arighna.